Any questions?
No, I think I underestimated the cleverness of the indexing in problem 3 on the midterm a little bit, but I don't know how clean can it be there. It seems like it should be able to be expressed cleanly versus brute forced explicitly with a min-max function to determine the indexing of, say, A in terms of L.
Let me see what you're talking about.
I think I'm probably just being dense this morning with it.
Oh, I need to share, right? All right, so what were you saying?
So it's in A in part 3 here, where it's to write A in terms of L.
Yeah.
And so when you go to index into L to form A, you're multiplying these terms, and some of the terms they're transposes of the others, so the indexing flips on them. So for instance, if you were to compute A at row 3, column 2, the indexing is reversed for row 2, column 3.
Right.
And so I guess I'm not seeing yet this morning how to clearly express that short of taking and using something like min or max to determine which index gets plugged in for the column or the row.
Oh, don't worry about that. Just, we know that A is symmetric, so you only have to give me, let's say, a lower triangular.
Okay. The lower triangular and then the diagonal case separately. Yeah. Okay. Was that the intent? I mean,
yeah,
am I
because
just being a little slow on the uptake of how to express the entirety of A?
no, it's just because you're going to use those formulas to figure out L, right? To kind of iteratively solve for L.
Oh, okay.
So you don't need twice the same
Yeah.
formula. I mean, you only need one of them. That makes sense?
Yeah,
It's like
that'll be good.
redundant. Yeah, it's like redundant.
Right. Thank you.
Other questions? All right, so let me see where we're doing. I was trying to do an example of the pseudo-inverse in action, right? So let's try to compute the pseudo-inverse of the Laplacian. So here I recall, say you have a bunch of nodes, and then pairs of nodes are called edges. And then the Laplacian has this form, the diagonal of degrees minus the adjacency matrix. Probably should write those things. Right, the difference of those two, or you can write it as a sum of outer products, one per edge. And these outer products are like the Laplacian of a very simple graph that has n vertices and just one edge from x to y. You just can add them all up to get L. Then this form also says that you can decompose L as B transpose B, some kind of square root. it's a rectangular square root. This matrix B, it's got a row per edge, and then the columns are indexed by the vertices, and it's called a gradient matrix. The action of this gradient matrix on functions, on vertices, is to basically take the values at the endpoint, subtract them, and assign the difference to the edge. Right? So that's B of H. It's what we could think of as a discrete gradient for the function H. Now, there's a slight annoying thing that if you want to keep here having one row per edge, you need to pick an orientation, because otherwise so you make an arbitrary choice of orientation. You're not making this into a directed network. It's still undirected, but it's just for convenience of indexing. If we want to index over the edges, well, we need to choose an orientation, just because this difference would change sign otherwise. All right, so now the transpose of B is the divergence. In other words, it takes a flow, which is a function on the edges, and gives you its divergence, which is defined as the flow out of X. To see this, maybe the best way to see this is to just do the sigma notation. So B transpose F at X. So B transpose is going to be V by E, right? F is a flow, so it's E by 1. So when you do sigma notation, the counter is going to run over the edges. And because we have oriented them, so they are of the form. Okay, so we orient over the edges, then we take B transpose. It's going to V by E, but X is fixed, so it's going to be X E, and then F. That makes sense?
Yeah.
All right, so now, remember the transpose just switches the order. So I'm going to turn it into B here. And remember, the rows of the matrix B are those differences of indicator functions, right? And so basically, if you fix X, so BEX is equal to 1 if E is of the form YX. So if, in other words, if the oriented edge E points to X, -1 if E is of the form XY, when E points away from X, and it's 0 otherwise, right? So in this sum here, as we run over all possible edges, And I think it's a bit sloppy here. X is fixed, so these are actually kind of other dummy variables here, prime, y prime. So as you run over all the edges, this is going to be 0 most of the time, b, e, x, right? Except when an edge either points to x or comes out of x. And in that case, you either get a 1 or a minus 1, right? So in fact, you're going to get a +1 every time it comes out of x, right? And a -1 every time, sorry, a +1 every time it points to x, and -1 every time it comes out of x. So actually I made a mistake. There's a minus here. It's not quite the divergence, it's minus that. Right? So it's going to be sum fxy every time y points to x minus sum yx. Sorry, getting confused now. If y points to x, oh, okay, yeah. Okay, so let's write it like that, right? We're summing over all the neighbors y where the edge points to x, f of yx, and over all the neighbors where x points away from, so where the edge points away from x, fxy. And then we use the property of flows and basically switch, these are different y's from those. These you can switch around as minus f x y prime. Then you got this, you leave. And this is the divergence of, well, minus the divergence of f. That makes sense?
Yeah.
All right, so why do I say all of this? Well, one of the most useful and important concept in this context is the notion of electrical current. And so, and how does the Laplacian come into this? Well, the idea, so let me just remind you a little bit. So you have a graph, right? Let me just make one here. I like the house graph as an example. And you pick two nodes, let's say A and B. And you think of the edges as carrying a resistance. So these are, little resistors that are hooked up. And the nodes are kind of places where you hook them up. You could think, maybe it's a light bulb. This is a fridge, etc. Right? So Um, and then you try to push some current through this network. Well, okay, let's do it this way. You try to maybe push, like, say, 1 ampere of current. And so you're going to have to use a battery or something and force a potential drop that makes this current go through the system. The potential drop needed, so the voltage needed to push 1 unit of current through the network is actually called the effective resistance. All right, and well, why? Because the idea is, from high school, you remember this kind of formulas like V equal RI, right? So voltage equals resistance times current. The current is 1 here, so in this case, the voltage needed will be the resistance of the system. And this quantity is incredible in the sense that it tells you a lot about the graph itself. Of course, again, if you've taken high school physics, you know that certain graphs are easy to reduce, right? Like you have the serial rule, for instance, which says that if your network consists of two resistors in series, then you can replace that, with just one that has the sum of the resistances. So this is kind of the idea. This is the effective resistance of this very simple P2 graph. There's also the parallel rule, which is a little more complicated. Yeah, so every resistor here has, an associated resistance, which you should think of it as a number associated to the edge. And but in general, like in this house example, how do you compute this effective resistance? Well, you can use the Laplacian. So this is where the Laplacian comes in. So let me just go through that. So so the key law that links potentials and current is called Ohm's law. So Ohm's law says that if you have an edge, xy, then the current, well, it's this thing here, right? The current is V over R, right? And the reciprocal of R, we can think of it as the conductance. 1 over R is the conductance. So, so the conductance from X to Y, and then the voltage drop. So this is the equation that links the flow, current flow, and to voltage potential. All right. For simplicity, let me assume here that let me assume that the conductance is 1 on every edge. It's not a big problem otherwise. All right, so let's try to rewrite this from our point of view. If C is 1, what can you say about the right-hand side in Ohm's law? What does that look like? Does that ring a bell? Hy minus Hx.
That was our gradient, right?
That was our gradient, right? So in other words, the current flow has to equal V times H from our point of view. But the other thing is that it's a current flow. So it will satisfy the node law. And the node law says that if X is not the source or the target, then the divergence of F of our flow needs to be 0. In other words, if you're not at the source or the target, whatever current comes into a node needs to get out of that node, right? So that's what divergence 0 means. Because when you sum it, if this is 0, then the pieces that come in equal the pieces that go out. Roughly speaking, is that. So, so that's the node law. That's another feature of current flow. And also, because we impose that we want to push 1 ampere of current through, we also have that the value of the flow, so the divergence of F at A, should be 1. And correspondingly, the divergence of F at B should be -1. Right. So with that information and the fact that B transpose is minus the divergence, so B transpose F is minus the divergence of F, right? This is a general fact for any flow. But in particular for us, that means that this has to be 0 everywhere except 1 at A and -1 at B with the minus. So the other way around, -1 at A and 1 at B. So in other words, we can write it like this, delta B minus delta A. Those are the indicator functions for those two nodes. Okay, so now let's put this together. Put those two equations together. And we get that B transpose B H in terms of the potential is delta B. And now we recognize this is the Laplacian, so LH. So that gives you an equation for the voltage potential. And it's a Laplacian system. Right? Unfortunately, the Laplacian is not invertible. Because if you take the function, the constant function, you're going to get 0. Right? The rows of the Laplacian sum to 0. So there's always this non-zero vector in the kernel. So the Laplacian is not invertible. But what we can do is we can take the pseudo-inverse. All right, so let's think about that. So what about all right, so we can do a couple of things. One way we could do it is to take B, right, and think of it as, so B is E by V, right? So it's going to go from RV to RE. In general, there's more edges and vertices. That's why I draw it like this. Of course, there's a kernel here. The span of the constant functions has gradient 0. Those are the functions that have gradient 0. And then over here, there's going to be some kind of image. And of course, we can form the SVD. So that's going to give us an orthonormal basis, V1, Vn. Actually, Vn. And we can even choose V1 to be the normalized vector of all ones. And also we'll get in the image, we'll get some vectors U1 and UN. And then some extra vectors. Now, of course, you might ask me if the kernel could be bigger, right? Why am I saying the kernel here is just 1? But that is okay if your network is connected. So there's actually, this is a claim that the kernel of B is 1 if and only if the graph is connected. Do you see why? You know, think about what does it mean to be in the kernel? Being in the kernel means that when you multiply B by this vector U, you get 0, right? That's the definition of being in the kernel. And so, but B is the gradient function. So this means that on every edge, you have U of X minus U of Y equals 0. So U of X should equal U of Y. Right? So on every edge, you look at the endpoints and the function hasn't changed. Right? Well, if you're connected, then that means that you can kind of form a path between any two points in the graph can be connected by a path. And if the function doesn't change along edges, well, then it doesn't change along paths either. So if G is connected, then this function U is going to be constant. So it's going to be in here. Right? And that makes sense?
Yeah, I think that connected.
And then how do you prove the other direction? Well, suppose G is disconnected. Here, if G is connected, then U is constant. Conversely, if G is disconnected, well, then it's going to have components, connected components, right? And you can play around with, so this is going to be some component V1, V2, I'll call it G1 and G2. You can play around with the indicator function of, say, the vertex set of G1. And the one that's 1 here and 0 there, and then the other one that's 1 here and 0 here. So, and G has connected components G1, say GK, then these indicator functions are, first of all, linearly independent, because you cannot write one as a combination of the others. That's pretty easy to see. Are linearly independent eigenvectors for zero, because they all have, they're constant here, so the gradient is zero everywhere. So they are in the kernel of the Laplace of B, of the gradient, and so in particular, you see the multiplicity of this. Oh, sorry. I jumped. So B is not square, so it doesn't have eigenvectors. And so they're gonna be eigenvectors for the Laplacian, but for B, they're just linearly independent vectors in kernel B. Right. So anyways, the dimension of the kernel is equal to the number of connected components. This can be shown. And all right, so now B, so L is B transpose B, right? And so and B, as we just saw, is sum J goes from 1 to N of sigma J Uj Vj transpose. Sigma J are the singular values. So and of course the let me see, I don't want to say. So I'm ordering the singular value from, so I want to order it so the sigma 1 is 0. Which is unusual. Usually the singular values are ordered in the other way. But the reason is because when I do L, B transpose B, you're going to get Bj Uj transpose, and then sigma I Ui Vi transpose. So J sum over I. And when you undo this sum, when you distribute, the Uj transpose Ui are going to be 0 unless I equals to J. So you get this. So that you immediately get the diagonalization for L. And if you write lambda J for the eigenvalues of the Laplacian, then here lambda 1 is going to be sigma 1 squared, which is 0. Right. So let's assume for simplicity that G is connected. So every other, every other eigenvalue is actually positive for J equal to. So then, as we've seen last time, how do you compute the pseudo inverse of the Laplacian? Well, L plus is simply sum j goes from 2 to n of 1 over lambda j. Right? And in particular, then L plus or L plus L, it's not the inverse, it's not the identity, but right, the 1 over lambda j cancel with the lambda j, so it's the sum of the Vj transpose. That's the span. It's the span of all the singular vectors except for the first one. Right? So the picture, it would be, you know, some kind of space here. The orthogonal complement to the kernel of B, which is also the kernel of L, right? The kernel of B and the kernel of L are the same. That can be proved fairly easily. Questions? Sorry, by this I mean the projection onto that. This Vj transpose is, so V2 to Vn is an orthonormal basis for this orthogonal complement to the kernel. And so this sum of outer products is the projection onto that subspace. And any questions so far? All right, so let's go back to our problem. So to solve LH equal the dB minus dA. And remember, H is a voltage potential. So actually, you can always add a constant. So note H is well defined up to an additive constant, right? You can add a constant to a voltage potential and not change anything, because how does it enter? It enters through the Ohm law. So it gives you the current by taking the difference. And so if you add a constant here on both ends, it will just cancel out, right? So it's not going to do anything. In particular, you can always ground the voltage potential the way you want it, either by setting it equal to 0 at A. That's a common one. It's a common way of normalizing. So you can assume H of A is 0, or you can assume that H of B minus H of A is 0. You know, that's another way to normalize it. And if you do it in that way, then H belongs to this space here, you know, V2 through Vn, right? Because it's going to be orthogonal to the constant function 1. And so if you apply, if you multiply both sides by L plus, then here you're going to get the projection of H onto the orthogonal complement to the kernel, but it's already in there, right? So then you're going to get, so with this, let's call it star. So with star, you get that H is equal to, right? So in particular, if you want the effective resistance now from A to B, you need to compute the voltage drop, the effective resistance. Remember, that was HB minus HA. Right? So that you can compute that by simply doing delta B minus delta A transpose L plus delta B minus delta A. So this is the quadratic form for the pseudo-inverse applied at in this vector here, delta B minus delta A. Now notice, since L is symmetric, L plus is also symmetric. And because L is positive semi-definite, L plus is positive semi-definite. Right? If you take the reciprocal of positive numbers, you get positive numbers. That's L plus is over here. And so in particular, you can define a square root of L plus. So by taking the square root of those lambdas, which are the sigmas, that we were talking about before. So you could rewrite this as L plus to the 1/2 applied to delta B minus delta norm squared. Which is a useful observation sometimes. I think I ran out of time, but at least I gave you an example how you could use the pseudo-inverse kind of in a practical situation. Any questions? I'm afraid I went too fast. I don't know. I just got a little excited.
No, I think well, I'm sorry, what was that last thing you said?
No,
You
go
got a little
ahead.
excited?
Yeah.
Oh, no, I think the structure of how that went was pretty straightforward. I think for me to fully take it in, I'd go back and watch Friday's lecture with this one. So maybe in that sense, it's a little fast at the moment, but I think it was perfectly paced for the level of involvement that was here. It was pretty straightforward, it seemed.
All right, let me know. I'm gonna stop the recording right now.